All right. Good afternoon, good evening, everyone. It's a pleasure to have Matt Kafker with us today. Matt is a PhD student at the University of Washington in Seattle. Actually, he's almost finishing submitting and being done up by fall or so, and then proceeding for a postdoc. His main area of research is theoretical nuclear physics. But actually, even before that, Matt has been with us since 2020. Started off with the first Wolfram Summer School on physics, the physics track, and since then he has been working on many body systems, computational many body systems related to causal graphs and condensed matter. And since then, Matt has developed an interest in many body systems, condensed matter, and computational physics. And some really interesting work happened regarding these hard spheres, which he's going to tell you about. The paper has just gotten published. You'll get the links to that. And it's a pleasure to have you
The
once again,
preprint,
Matt.
the preprint is published. The paper is
Oh,
not yet
sorry.
been published.
Sorry, the paper's accepted. I stand corrected. The
No,
paper's
it's not
accepted.
accepted.
The,
It's
re- the reviews seem to
the
say that.
initial reviews are positive. I don't want to jinx this. There's still a little bit of work to do.
Okay. Well, okay. That's we'll go with that. Okay.
Yeah.
Well, pleasure to have you, Matt. Floor is all yours.
Yeah. All right, let's do it. So now let me see if I can share my screen, which I probably should have been doing during the introduction. Um, Allow. Okay, can people see the talk?
Yes.
Okay, and I have now moved your faces over in this direction. So if you see me looking over here, I'm looking at the chat and I'm looking at you. And my slides are right in front of me. Let's see. Yes, I said this 2 seconds ago to everybody, but I'll put it on the record. Please interrupt. It's much more fun that way. And since it's your third talk of the day, this can be a conversation and it doesn't have to be me droning on at you. Um, let's see if there's other logistics. I'll try to attend to the chat as I go, but we'll see how I do. So yeah, please interrupt. Okay, so my name is Matt. I'm from the University of Washington in Seattle. I'm in the physics department. I have some unknown relationship with the physics project here. I've written affiliated research fellow. That term was once a thing. Now, who knows what it is? But I come and I speak at the summer schools and the winter schools. My collaborators on the work that I'm going to talk about today are primarily Xerxes, but also Christopher Wolfram back in the day, 5 years ago now, which is crazy. The title of this talk is Non-Equilibrium Dynamics of Many-Body Systems and the Wolfram Physics Project. So we're going to sort of cover a ton of ground here. I've been reflecting on this. 2 hours is like a strange amount of time because if it was 30 minutes, then we could just do results. And if it was like 8 hours, then I could teach you everything from the ground up. But 2 hours, we're going to have to try to find a balance, and I'll do my best. But together we will navigate to somewhere useful. Um, okay, so if I can figure out how to advance. Okay, so I just finished the 5th year of my PhD, I guess. Um, I've been a quote unquote member of the physics project since 2020, although the specific title is ambiguous. I started using Mathematica in 2018 when I took a statistical mechanics class as an undergrad, and that was pretty hardcore. And I needed to step up my integral skills. That's what got me started on this. I'm going to talk about nuclear physics a little bit because that's my day job. But I promise we will get in and we'll get out. And most of the time we'll spend talking about hard spheres and related things. And I want to stress that I am not a Wolfram physics expert. And if you have specific questions about the Wolfram model and so on, I'll direct you to Xerxes. And I see Nick is here as well. So I want to make very clear where I'm coming from here. So I started this work in June or July of 2020 in the middle of the pandemic in my room in Eugene, Oregon. And this talk, I've been giving versions of this talk every summer and winter school basically since then. And this one is kind of interesting because now the paper is very close to done. I submitted to Physical Review E, and the initial response from the referees was positive, as I just pedantically corrected Xerxes about. I'm not sure whether that was necessary, but I did. Paper's not accepted, but it looks good. So this is really exciting for me because I've been working on this for longer than I've been working on my PhD, actually. And the fact that it's turned into an actual scientific paper that grew very linearly and directly out of work done at a summer school. Maybe that can at the very least, that can serve as sort of an example. If you all are working on something and you're convinced that you can write a paper, you can write a paper, and you'll probably be able to do it faster than me. Um, and if people have questions more generically about the journey of sort of doing this, going from a summer school to a paper like this, I'm happy to talk about that as well because I've had a long time to think about it. Let's see. Yes, positive reaction from referees. Yes, agreed. Um, I have had much worse responses from referees to papers than the response to this paper. So I believe it will be published. I just not trying to not jinx it. Okay, so outline of the talk. I'm going to talk about nuclear physics. I always like to start the talk doing this. We'll spend about 20 minutes here. I think it's interesting. I'm going to give you more tools than we'll have time to cover in detail. Excuse me, so that you can start exploring yourself. I'll also distribute a copy of the slides immediately after the talk on Discord. And broadly speaking, there's a lot of text on these slides, so they can also be viewed as a set of like quasi lecture notes from which you can get a more or less complete, not complete, but very detailed understanding of the topics we'll cover. So I'll say that. We're going to go over hard spheres, what it is that we're talking about, talk about sort of the basic physics of these things and how you simulate them. And then we'll transition to specifically a Wolfram physics kind of perspective, Although I will say that if you are here as like a deep skeptic of the Wolfram Physics project, that's totally fine. I suspect that doesn't really describe many of you here, but every single thing that we're talking about can stand parallel to the physics project and on its own merits. But it has a sort of synergistic relationship with the physics project. So I'll clarify what I mean by that. And then this last point, so that's the network-based sort of approach here. And then this last point is what the meat of the physics is, and this is what the paper is primarily about. We'll talk about non-equilibrium dynamics of these systems. I'll say explicitly what that means, and various kinds of relaxation phenomena and the sort of causal perspective. Yeah, I've mentioned already, you can chime in at any time if you have questions. Nuclear physics, this is going to be 20 minutes, but Xerxes, you need to keep me on track for 20 minutes. Here, why don't I'll set a timer for myself just so I can make sure that I don't screw that up. Okay, so I have my list of collaborators here. Oral is my PhD supervisor, but I work very closely with people at Los Alamos National Lab, and then I have collaborators all over the world and also in the technology space. This is a snapshot of a nucleus as it is at the moment of scission during the nuclear fission process when it splits in two. Okay, so let's just talk about nuclear physics for a while. On the right here, we have sort of the standard reductionist picture of the matter around us, which is made out of molecules, atoms, and then plunging deeper into the structure of these things, you get nuclei, protons, neutrons, and then the internal structure of these things. The red square is where I live. And in some sense, it is the most boring part of this diagram, stolen blatantly from Google Images, but in fact, that's a bit of a disservice. Low energy nuclear physics is very nice science, broadly concerned with interacting quantum many-body physics. That is the general sort of framework in which we work in nuclear physics, and there's a lot of interesting questions to discuss. So this is the picture of all matter on Earth, which has emerged in the last 150-ish years, very roughly speaking. I'm not going to talk about high energy nuclear physics. I think I saw in the introductions that we have some people who have thought about nuclear physics before, so feel free to chime in if I get something wrong or if you have comments to add here. So I'll draw your attention to this picture on the right here. This is the nuclear chart. It's basically the nuclear physics analog of the periodic table of elements. So on the horizontal axis here, we have the number of neutrons in your nucleus. On the vertical axis, we have the number of protons. And then these colored squares here are the set of nuclei that are known to exist in nature. So at the most basic level, they're defined by the number of neutrons and protons in the nucleus. And then they're colored in according to their primary decay pathway. So the black squares are stable, but you have various kinds of beta decay, that's the blue and purple, and then you have alpha decay is the yellow, and then you have fission, which is the green that starts to occur up here. And there's proton emission. There's a few others, but the point being that this is a very there's a large space to explore here, is I think the point that I'm trying to get across. It's an interesting problem because we have two types of fermions, whereas in chemistry you just have electrons. We now have protons and neutrons to keep track of. And let's see, there's all sorts of questions you can ask about these things. So for example, why is it that these are the prominent decay pathways? What does it mean to say that a nucleus undergoes fission or alpha decay or beta decay or something like that? It's not straightforward. Why is this the particular pattern that you see? Nature is complex. There are more questions here. So people can see my mouse, by the way, right? Okay, so you common questions to ask are: what are the binding energy of the nucleus, nuclear radius, structure, excited states, dynamics, etc. Nature is complex. There are some trends clearly visible from this picture, but to have a detailed ability to predict this requires a quantum mechanical framework. And in fact, it's a very difficult problem because it's a strongly interacting quantum many-body problem, sometimes out of equilibrium. Nuclear fission, which I'll touch on briefly, is out of equilibrium. Um, and lots of people work on this from a lot of different perspectives. I'm going to look in the chat here. Okay, Dugan, I like your message there. I didn't know that. That's cool. Okay, so why care about nuclear physics? I guess I'll just say briefly, there's a handful of very interesting and fundamental scientific questions which nuclear physics aims to understand. The first of which is, what is the origin of all the elements we see in the universe around us? Some of them, actually, many of the light elements, it's basically understood where they come from, nuclear synthesis inside of stars. But as you get to the heavier elements, this starts to become much more of an open question. And it is believed that the heaviest elements are going to be synthesized through something called the astrophysical R process, where, say you have a supernova or a neutron star collision or something like this, it ejects off a bunch of very neutron-rich matter, which is then captured inside nuclei, and then they alpha decay and fission and things like this. And it is through this process that's believed that the heaviest elements sort of come to be, but in fact, it's not precisely known where in the universe in particular this happens. So it's known that you can have R process nuclear synthesis in supernovas and neutron star mergers, like I say, but specifically which process is responsible for the abundance of heavy elements that we see in the solar system, for example, that's still an unknown question, and people are actively working on this, which is pretty cool. So that's one question. Then there's another question, which is, what is the heaviest element that can possibly exist in nature? So interestingly, there's a very practical definition of what it means for an element to exist. That's this fourth bullet point here. An element is said to exist if it can live long enough for the electrons to relax into shells. So it needs to live for about 10 to the minus 14 seconds, which is interesting. And it means that the periodic table is still growing. The last element was added to it in 2002. This is oganesson. And it's a big theory, computation, experimental effort involving scientists all over the world to address this question of what is the absolute limit of this, and can we keep adding elements to the periodic table? And then there's this final question. I'll say one more comment about this, just because I think this is a funny story. So oganesson lives here on the periodic table, which you'll notice is in the noble gas column of the periodic table. So I was attending a lecture by an experimentalist who works on super heavy element synthesis, and I said, okay, so oganesson is in the noble gas column of the periodic table. Is it a noble gas? And her response to me was, we have made 6 total atoms of oganesson ever. So unclear. That's not much of a gas. So that's entertaining anecdote of me being sort of silly. Right, and then this last problem here is
A quick
as
question.
interesting as the others. Yeah, please.
I'm just curious, what do you mean with relax into shells? I mean, usually we talk about orbitals of electrons, so like shell sounds like the Bohr atom. So I'm just kind of
Oh no,
wondering.
I mean orbitals. Like you need the basically the electronic shell structure to form. By shell, I guess I just mean the electrons arrange themselves into orbitals, and those orbitals are often separated by gaps or something like that. So that's all I mean by shells. But yeah, orbitals. You need the electrons to relax. That's the operational definition anyway. Yeah, and then sort of this last point is here is what the heck is going on inside neutron stars. The more I do nuclear physics, the more I'm convinced that is like one of the coolest unanswered scientific questions out there. And I encourage people to go start reading about what the heck is going on inside neutron stars. Okay, so I wanted to talk about, okay, so I've still got time on nuclear physics. So what I want to do is I want to start to make an actual step into this space and start to give you an idea of how people start to think about these questions. How do you actually calculate in detail properties of nuclei? Because I said it's very complex. The nuclear chart is very complex. There's a lot of different patterns at work here, and you have a strongly interacting quantum system with many particles. As I'll hope to communicate, that's a super difficult problem. And people have been thinking about this for over 100 years now. So there's all sorts of different ways that you can sort of start to navigate your way in. The first, let's say, most principled way is we might just want to solve the Schrodinger equation, right? Because we have a quantum system. Solve the Schrodinger equation for all the particles, but in most cases, this turns out basically to be impossible. For heavy nuclei, it's particularly clear because you have a many-body wave function, and for a system of many particles, your many-body wave function is a function of n coordinates. So, for example, if you take a uranium-236 nucleus, you have 236 particles in it, so your wave function is a function of 236 variables. So even writing down the data to represent that function in certain configurations is mathematically intractable. So that's basically a non-starter, although there are various ways that you can sort of try to approach that from different directions, which I can talk about. So the first place, the simplest place that people started, well, I won't make a historical comment, but a very simple place to start. We have a bunch of interacting particles. There are familiar physical systems which have a bunch of interacting particles. These are known as liquids. So we'll start by treating the nucleus like a liquid, with the additional observation that the nucleus has an electric charge. So this charged liquid drop model of the nucleus is something that people have been trying to use since the 1930s. And as far as ways into the subject, it's relatively simple. So this is the liquid drop model. The energy of the liquid drop model is determined by a number of terms and associated parameters. These little a's are parameters that are fitted to experimental data. So let's talk about the meaning of all these things. This E is the energy of the nucleus, okay? And N and Z are the neutron and proton numbers, respectively. And if you take their sum, that is A, which is the total number of particles. And you see capital A appears a bunch of times in this formula, okay? So
I have a question.
Yeah, please.
So do the protons and neutrons maintain their identity as particles within the nucleus? That is, they're made of quarks, right? And so like, do they exchange quarks at all?
Yeah, so we're going to be working at sufficiently low energies that you don't have to think about quarks. You can think about the protons and neutrons as fundamental particles for the purpose of this discussion. A slightly more precise argument is that a proton or a neutron in size is about 1 femtometer across, 10 to the minus 15 meters. A quark is about 10 times smaller than that. And so you need high sort of relative momenta to even resolve those kinds of things. And low energy nuclear physics, which is what I'm going to be talking about, you can very often, almost all the time, in fact, in certain kinds of considerations, get away without thinking about quarks because the protons and neutrons behave as fundamental particles inside the nucleus.
Okay, great.
Does that answer your question?
Yeah.
I'm not saying quarks don't exist, but I am saying you can do quite a bit without having to think about them. Okay. Right. Okay. So let's take a look at this formula in detail. So E is the energy of the nucleus, N is the neutron number, Z is the proton number, A is the total number of particles. So this first term here says that there is an energy just associated with the total number of particles here. Another thing that's worth keeping in mind is that very loosely speaking, the nucleus, this is sort of a cartoon picture, looks like a sphere packing. So the volume of the nucleus is going to be roughly proportional to the number of particles. So the volume of the nucleus is proportional to A here. And that means that the radius, that's the second equation here, is going to go like A to the 1/3. Does that make sense to people? Yeah. Okay. So this first term is often called the volume energy, and this coefficient is negative because this is it serves to bind the nucleus. Then we have a to the 2/3, which looks like, given that the radius goes like a to the 1/3, this starts to look like a surface area term, and this is the surface energy. And then we have a z squared over r. That's this third term. This is the Coulomb energy, because obviously we have a bunch of positively charged protons crammed inside this thing. And then there's this term here called the symmetry energy, which is quantum mechanical in origin. And I was just reading a paper about this, has all sorts of implications for our process astrophysics and neutron star structure and the limits of stability of nuclei and all these things. So there's all sorts of good stuff going on inside the symmetry energy term. But basically, you can think about this as seeking to balance the number of neutrons and protons inside the nucleus so that you have n approximately equal to z. And then you can go out and you can measure the energy of a bunch of nuclei, and then you can fit these parameters to it. And what you see here, I'll direct your attention to this figure in the bottom right corner here. So we have on the horizontal axis A, the total number of particles inside the nucleus. And then on the vertical axis, we have this thing B over A, which is the same thing as this E over A, is the binding energy. And the black curve is the liquid drop model, and the white dots are some experimental data. So all this to say, this is very good. Now, there's all sorts of interesting physics having to do with the deviations of these data points from this curve, but it's a really good starting point. You don't have to know any quantum mechanics, for example, and you don't have to have a supercomputer. I encourage you to, make a little Wolfram notebook and start playing around, because you can it's very easy to compute with this thing, obviously. So a little bit more data. This R0 is a proportionality constant here. It's 1.2 femtometers. So the relevant sort of scale for the size of a nucleus is 10 to the minus 15 meters.
Sorry,
And yeah, please.
can you repeat what's the meaning of B over A, please?
Yeah, so B here is precisely the same as this E in my top equation.
Okay.
It's exactly the same, but you just divide by the particle number, because you might imagine a uranium nucleus, which is huge, has way more total energy than a oxygen nucleus, which is much smaller. But if you divide by the particle number, you can sort of compare apples to apples in that way.
Yes.
One thing that is interesting, if you look at the vertical axis of this figure, energy units are measured in mega electron volts, typically in low energy nuclear physics. And you'll see that this only extends from 7 to 9 mega electron volts.
It's like energy per unit of mass.
Yeah, or per particle.
Okay.
Yeah.
Thank
Yep.
you.
The just to finish off that last thing that I was saying is that this is approximately constant. Like if you made this scale go from 0 to 10 instead of 7 to 10, this would look almost like a flat line. And that's one thing that's interesting and not self-evident about nuclei, that the binding energy per particle is approximately constant, but there are some nuclei that are more deeply bound, so this energy is more negative than others. And the peak of this curve, by the way, is iron 56. Some of you will have heard that stars will fuse nuclei in their core until they reach iron, at which point it becomes unstable and then some explosion happens or something like that. The reason is because iron is the most deeply bound nucleus, and that's something that you can see using the liquid drop formula. And I will say I have this bullet point at the bottom here. This is a reasonably good fit for all nuclei with small deviations, but if you use a slightly more sophisticated version of this picture that I'm talking about here, but not by much, like, there's a few correction terms that you add, you start to get to the point where advanced quantum many-body approaches cannot make as accurate predictions for the energy as this very simple model here, which is kind of interesting. And it gives you a sense of how hard the theoretical problems that modern nuclear physics is trying to accomplish, in fact, are.
Is this model for one particular atom?
No, this can be applied for the entire nuclear chart. So you can go to every single nucleus in this picture here, and you can calculate the energy just using this formula. And in fact, you can ask even more questions like, what if I make a super neutron rich nucleus and it's somewhere out here in this space here? What the hell happens? And in fact, people do precisely this. The point is that this is a general purpose tool, which is essentially like phenomenological in character. Like this is not really consistent with the principles of nature as we know them, which is quantum mechanics, blah, 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 but it's very useful. And in fact, it's surprisingly hard to beat these kinds of formulas.
No, we should be so lucky. Okay, so what's interesting is that the size of the that 1.2 femtometer size of the nucleus that's the radius. And
Yeah, that's right.
that's not much bigger than the size of a single proton.
Well, so remember that it has this a to the 1/3 factor that multiplies the 1.2. So
right, okay.
right. So the total radius of the nucleus, this R here is 1.2 Fermi or femtometers times the cube root of the radius, that formula basically follows directly from if you just like had a sphere packing something precisely like this. It would be like the size of an individual sphere times the cube root of the number of particles inside your
Okay, yeah, that makes
bag
sense.
or something.
So
yeah.
Capital N is the number of neutrons and capital D is the number of protons.
Correct. Yep.
Okay.
Yep.
All right, I'm happy.
All right. And by the way, I have my email on the first slide and I'm on Discord. So message me after if there's more stuff that you want to discuss and it's too much to get in the weeds now. I see that somebody else wants to talk. So go ahead.
Oh, no. I was just going to ask, like, is this, as Stephen may say, is this a well-known thing in chemistry?
Can you say more why you're asking that question?
Oh, I was just, never mind. I'll
No,
say
I mean,
Well,
it's a perfectly
yeah,
it's
I
a
mean, I would
perfectly
say
valid
that, like,
question. Go ahead.
if I can hazard a guess, I would say that chemistry is more on the level of how are the electron shells interacting with each other, and that's pretty far away from the actual nuclei. All you need to know about the nucleus is sort of like how much mass it has. That's just a guess.
and the electric charge, right? So chemistry, the way that people think about chemistry in my neck of the woods is that chemistry is an interacting many-body problem among the electrons in the atom sitting in the Coulomb field of the nucleus. Nuclear physics is a separate problem, which is an interacting many-body problem where it's just the nucleons exerting force on one another. And how do you calculate the energy of that system is a separate question from how you calculate the energy of the electrons. This formula is just for the nucleus and is pretending that electrons don't exist. Because you have to remember the electron cloud is like 5 orders of magnitude. Let's see, an atom is roughly an angstrom, which is 10 to the minus 10 meters in radius. And this formula is telling you that the nucleus is 10 to the minus 15 meters in radius, right? So you have vastly different scales of physics taking place here.
So that's
Okay.
about 100,000 scale from the electron shell to the nucleus. 100,000 times.
That's right.
My goodness. I knew it was smaller, but okay.
Yeah, it's crazy. It's crazy. And I have one further remark about that going forward. Xerxes, can I take 25 minutes on nuclear physics? I'm at 20.
Okay, fine.
Okay. So I'll move more quickly here. So this just to say you can do a lot of work with this formula. One thing that might be interesting for you to see is you can apply this to nuclear fusion reactions, like the kind of stuff that they do at the National Ignition Facility. I've stolen a picture from their website here. You have some tiny piece of hydrogen, deuterium, and tritium that's the size of a grain of rice. You bombard it with this enormous pulsed laser. And then you are trying to accomplish this nuclear reaction here. The liquid drop formula is known to be inaccurate for light nuclei, but you can get a sense for why this works if you just calculate the energy of the left-hand side and the right-hand side, excuse me. You can see that the helium/alpha particle that's released from the nuclear reaction is much more deeply bound than the constituents going in, and it is precisely that binding energy that's released in the fusion reaction. So I'll let you explore this for yourself because we're short on time, and I have there's a little bit more to say about nuclear physics. So I wanted to say a little bit more about the quantum many-body perspective. So a nucleus is a fully quantum object. More sophisticated approach is to treat the neutrons and protons as independent particles moving in some potential, in which case you can solve the one particle Schrodinger equation. And now we're back on somewhat familiar territory from our undergrad quantum classes. And the underlying hypothesis behind this approach is that the cumulative effect of all of the crazy forces that the protons and neutrons are exerting on one another is to create a mean field in which the particles move. So an average force that the individual particles feel. A typical parameterization is something like this Wood-Saxon potential here, which is plotted below. So we have distance from the origin as a function of space, and then this potential. It will look something like this, and you can imagine that some negative potentials, you can have various bound states that sit inside this thing. A slightly more sophisticated approach is to take this Wood-Saxon potential and then add a spin orbit term, which will be familiar to some of you from quantum mechanics. And if you combine these two things together, you can reproduce the so-called shell structure of nuclear physics, which is depicted on the right. In particular, you have a bunch of particularly stable nuclei. So if you look at the rightmost column here, this is a single particle level scheme for a potential that looks like this one here. And the way that fermions work is you start by putting particles in the lowest level shell, and then you occupy the next one, and then you occupy the next one, and so on. And what you'll see is that these shells sort of arrange themselves into clusters. So you have one level that's right here, and then it's separated by a gap, and then you have two levels, and then there's a gap, and then there's three here, and so on. And the particular numbers of particles associated with these shells are called the magic numbers, and they're listed on the right here, 2, 8, 20, 28, etc. And these are the nuclear physics analogs of the noble gases. So atomic shells, like I was just speaking about a few minutes ago with, is your name Damaris? Okay, good enough. Sorry, I'll do my best. The noble gases are atoms with sort of closed shells precisely like this. So these are called the magic nuclei, and they have this pattern here. So anyway, that won Gopher Meyer the Nobel Prize in the 1950s for working this out. If you want to talk about fully quantum many-body physics, I'm going to lightning breeze over this because it's way too much material to cover in any depth. The proper way to do this is you write down a Hamiltonian for your interacting many-body system in quantum mechanics, which has some kinetic energy. It has some two-particle interaction, and then maybe there are more interaction terms. And then ideally, you would find the eigenstates of this system, but that's a super difficult problem. This is some crazy differential operator and a bunch of variables and things like this. So what you typically do is you assume a form for your many-body wave function. Here I have a Slater determinant. You minimize the energy. So you have your Hamiltonian, you minimize the energy. That gives you a set of coupled nonlinear integral differential equations, which I've written here. So this is some insanely complicated mathematical problem, coupled nonlinear PDE system, which you get if you want to try to do this properly. I'm sorry to say that I'm running out of time here, but a version of this is what we do. So the modern approach to this problem is density functional theory, and it's some approximation of this stuff that I went over way too quickly on this page here. So on the right, I'll just give you a sense of what kinds of things we can calculate. So this is the fission of a uranium nucleus, uranium-236. This is work that comes from my group that we published in PRL. And this is a slice through the number density of neutrons as a function of time. Time is moving down the page. You see that as the nucleus starts to break apart, there's sort of this low amplitude cloud of neutrons that are released. This is presented in a logarithmic scale. And there's a whole physics story behind this that dates back to 1939, which I can talk about if people explicitly ask me. Yeah, this is the story of density functional theory. And I'll just say, because people are really interested in computational thinking at these schools, this particular calculation on the right, you have to solve many, many coupled nonlinear PDEs. So the figure to the right was a very high accuracy simulation. It required solving 4.4 million coupled nonlinear time-dependent PDEs. Which required using 27,000 GPUs at once and maxed out the biggest supercomputer in the world in 2022. So that's pretty cool. Now there are bigger computers and people have done bigger computations, but at the time, this was a candidate for the biggest numerical calculation in history. Okay, so serious business in nuclear physics, but unfortunately, unless people explicitly ask me, I'm going to move on. And I just want to say, Wolfram Physics is claiming to have some new things to say about quantum mechanics. That's fantastic. I really encourage people, if you're taking this aspect of the project seriously, to try to reproduce some of the things that have been discovered in the last 100 years in nuclear physics. So can you diagonalize a 3D harmonic oscillator? Can you solve the Wood-Saxon potential? Can you solve an infinite cubic well? Can you find the spectrum of the hydrogen atom? Things like this. These are questions that should be answered, in my opinion. I don't know if people have actually worked on this. I don't think in much detail, but in any case, that's my challenge to you. Feel free to take it if you're inclined to do so. I see that somebody loves seeing logistic curves. Yes, the Wood-Saxon is, yeah.
Matt, a really
Okay.
quick
Yeah, please.
question, to the pictures you just showed of the 236 uranium. Are we seeing
Yeah.
the splitting of the nucleus in this picture? Is that what we're
Yep.
seeing?
So this is the actual splitting of the atom. These are basically, I'll make a slightly controversial but not too controversial claim that these are the highest accuracy simulations of the fission process that are available. And I have the reference on the bottom of the screen. I also have a link to my website on the first page of the slides where you can read the entire paper if you want to see it. Yeah, unfortunately, there's 100 hours of lecture to be had about these nuclear physics kinds of things, but we're having too much fun. So
Yeah, just one quick follow-up question is like,
yeah.
Can you tell from these simulations, like what is the main thing driving the separation?
Yeah, so for these particular things, so it starts in a deformed state, like in the top frame here. And you have a large Coulomb repulsion between the two halves of this peanut-shaped thing. So you have electrostatic force, which wants to drive this apart. But as we remember from our discussion of the liquid drop model, there's also a surface energy, which wants to restore this to a spherical shape. And it was understood as early as 1939 that it is primarily a competition between the Coulomb force, which wants to blast the nucleus apart, and the surface tension, which wants to keep it spherical, that governs the fission process. And just to say a little bit more about this, if you have a light nucleus, then the surface tension will broadly win. And if you deform it to be like an ellipsoid or a peanut shape or something like this, it will want to snap back. But if you have enough particles inside it, at a certain point, the Coulomb force will win that battle, and it will spontaneously deform to a shape like, or it'll like absorb a neutron or something like this, and it'll deform into a configuration like this, and then the Coulomb force will just win and it will blast the thing apart. I see that Flo has a question. Please go ahead.
Yeah, on the slide with the liquid drop model, you said that even modern methods, it's like hard to beat that simple equation. Was that 4 million coupled PDEs? Was that doing the same thing? And if so, like how do the two compare in terms
So
of
it's a related, yes. So these 4 million coupled PDEs, this is a time-dependent problem, which is trying to do slightly more than calculate the energy of the nucleus.
Okay.
Having said that, it's very closely related. And if you basically do the static Schrodinger equation instead of the time-dependent Schrodinger equation, like to zeroth order, that's what you're doing, then you can calculate the energy of the system. And yes, it is precisely these methods, despite the complexity of this mathematical problem. I'll be a little bit more precise. The RMS, so like the root mean squared deviation of the energy from the experimental value for a density functional theory approach, which is like these coupled big nonlinear crazy systems, it's something like 3 mega electron volts across the nuclear chart. So that'll give you a sense of like the accuracy. And I was just reading a paper a few days ago about a liquid drop model precisely like this, which gets you, you add a few more terms and it gets you less than 1 MeV of accuracy for calculating the energy across the nuclear chart. So when you do density functional theory, you have all the wave functions, so you can do more things, but it's such a hard mathematical problem that the accuracy you do better if you're just using a liquid drop formula like this. So
yeah, you have 4 million more equations and you get a worse result. That's so
yeah, that's
sad.
right. That's right. It's tough. I mean, it's exciting and it's an opportunity. Like I said, this is really cutting edge science, and you need giant supercomputers and really advanced theoretical techniques and the whole thing. But it's crazy, like how good it shows you. Like the nucleus is really very much like a drop of liquid. Like that's a very good approximation, sort of an eerily good approximation, in fact.
It's like the definition of diminishing returns.
Oh yeah. Yeah. I mean, think about the amount of electricity. I mean, just running these supercomputers for a day, it's like insane to even turn them on. And then you have the GPUs whirring for many days in a row, and then you calculate the energy, and it's like, well, it's pretty good. There's a very serious scientific story here. There's a lot of scientific value to having microscopic simulations like this. However, it's a tough problem, and the progress is, we're making progress, but it's tough.
So
Thanks for
this
asking
is,
that question.
uranium
Go ahead.
236. I guess that's
Correct.
uranium 235 with the added like neutron that you like
Correct.
put in there
Yes.
to split it up.
Correct. Yep.
All right.
Yeah, so technically speaking, this is neutron-induced fission. These are great questions. I'm so happy that you're all asking questions. Let's talk about hard spheres and things like this. I did 32 minutes, Xerxes. I'm sorry. People were interested, so
You're
I'm
doing
not
great.
that sorry.
No problem.
Okay. All right. So those are the people that pay the bills. I have to mention nuclear physics, and I encourage you to please come talk to me after if you wanna learn more about this. It's a great subject. But let's talk about hard spheres, Wolfram physics, etc. And we won't come back to nuclear physics at all. So yeah. So hard spheres, this is the same kind of physics problem that we're interested in. Fundamentally, we have a system of particles, and they're going to be interacting with one another in sort of a strong manner, and we want to be able to predict the behavior. So let's say what explicitly hard spheres are. So this movie basically sums up everything that there is to know about hard spheres. Hopefully it's coming through over the Zoom call reasonably well. You have some particles, they have some finite extent in space, they move along straight lines, they bounce off one another. This is sort of the details, and then you can add a bunch of them in a box. They bounce around like this. Pretty non-controversial place to start here. So these are sort of a prototypical model of gases, liquids. There's a number of other things. You can use them to model colloids, granular materials, solids, glasses. We'll talk about the last two a lot over the course of this talk. Basically, they're particles which interact through a short-range, strongly repulsive force that's best captured by a pair potential like this. So you have the position of one particle and another particle here. And if you calculate the distance between them and it's less than 2 radii, the sigma is the radius of one of these circles or spheres. You can do this in any dimension. Then the potential will be infinite. Otherwise, it will be 0. Okay, so this is the starting point for these. This model. This is much simpler than the nuclear physics that we're talking about. This is probably the longest studied interacting many-body system in the physics literature. Published results going back at least to van der Waals in the 1870s, so that's 150 years. Also moderately interesting to know that when the first quote-unquote supercomputers, like the first real computers started to come online in the 1950s and being used for physics simulations, hard spheres were some of the systems that were being modeled then, which is pretty cool. Van der Waals won the Nobel Prize in 1910. And although this is highly simplistic in some sense, especially when you compare with something like what we're doing in nuclear physics, this is a widely used model. And it's not just being used by simpletons. There's actually a lot of rich physics here and unanswered questions, which we'll dive into in detail. Specifically, most of them surround a variety of different kinds of phase transitions. So at high densities, hard spheres can be in a solid phase, but they can also be in a glass phase, which is distinct from an ordered solid. In 2 dimensions, you can have a totally different state of matter called a hexatic, which is intermediate between a fluid and a solid phase. And then you can also have something called the Gardner transition, which is very interesting, and I don't understand it very well. I encourage you to read about that. And each of these transitions is going to be, each of these phases of matter is going to be associated with a phase transition. And I will also say that there's a lot of interest in pure math for these things. So the 2022 Fields Medal went to Wiazowska for her results on optimal sphere packing in 8 dimensions. I'm not a mathematician, so I only know the words basically. And that's since I think been proven in 24 dimensions as well. And also, yeah, that's right, E8. And then also there's the Kepler conjecture, which concerns optimal packings of spheres in 3 dimensions. That one is particularly remarkable because it was conjectured that a certain regular sphere packing would be the globally optimal way to pack spheres in 3D. And that was in like 1604 or something like that. And it was rigorously proven in 2017. Is insane. The person who did it was named Tom Hales, and he apparently used Mathematica in his proof. But it was quite a substantial thing. And I think it took actually something like 20 years from the first version of the proof until it was widely accepted by the community, because it was so long and so complicated that they had to build like formal proof systems, like computational proof systems to verify it. I'm super duper not an expert in this story, as you can tell by the way I'm talking about it, but that's an interesting history, and I encourage you to read about it if you care about these kinds of things. And also, if you go to very high dimensions, sphere packings are relevant for error correcting codes. So if you're a mathematics person, if you're an error correcting code person, if you're a physics person, there's all sorts of reasons to care about this, and it's not antiquated physics by any means. So you can also realize these things in experiments with colloidal systems of little tiny plastic beads suspended in some kind of fluid. I can direct you to literature on this if you care. I haven't read it in much detail myself, but I know it to be the case. It's supposed to be an approximation of the interaction between atoms or molecules, right? So that's largely what we're up to here. And although this is simple, there's no parameters in the interaction, which is something to be said for it. So if you think about for example, the standard model of particle physics has 19 free parameters, which have to be determined by experiment. The density functional theory we were talking about in the context of nuclear physics has 10 parameters. I have 9 there. I think it's 10. Whatever, we can quibble about the precise number there. And if you look at those pair potentials, like the force between two particles in nuclear physics, I was reading a paper the other day where one of the most accurate ones has 42 parameters just to specify the force between two particles, right? So this has no parameters. I guess the radius of the particle, if you insist, but that's not what I mean. Phenomena that are observed in these systems are very likely to be reliable in the sense that they don't depend on finicky details of how you specified the parameters or the potential, but whether they'll be observed in nature is a separate question because it's an idealized system. And I will say also that you can solve the equations of motion for this system exactly on a computer, but they're chaotic. So worth keeping in mind. Okay, so I'm now going to get into the specifics of hard sphere physics. Xerxes, I have no idea how I'm doing on time. I'm at 53 minutes roughly, is that right?
Yes.
Okay, I'll keep an eye on that. Right, so now we're going to switch to details of these systems. So rather than speaking at a very high level, we'll start to get very granular. I will say right at the beginning, if you look in the bottom left corner here, there's a function on the Wolfram function repository called hard sphere simulation, which came out of my 2020 summer school work. And it's pretty easy to use. So I encourage you to go play with that if I am able to convince you that this is fun and interesting physics, which I hope to do. And a lot of the figures in the coming slides have been made with that function, although the material that ended up in the paper has been made with a slightly more sophisticated tool. I'll talk about precisely the differences. They're in some sense minor, but important. Okay, so the first thing here, you have a hard sphere simulation, you have a bunch of particles bouncing around in a box, you have position, you have velocity, and you have these things as a function of time. Immediately, the question presents itself of what do I do with this? How can I start to learn about the physics of this system? How can I start to encapsulate this raw data into metrics that allow me to learn something? So the simplest thing that you can do is to make a distribution of the speeds. So this is a speed on the horizontal axis, and I've made a histogram of them. You'll find that the speeds are distributed according to a Maxwell-Boltzmann probability distribution. Here I have the magnitude of the speed, but if you have the velocity distribution, it's just a pure Gaussian. So this v squared comes from integrating over the solid angle, basically. And you see that I have some, I run a time-dependent simulation, I bin my velocities, and then I plot this Maxwell-Boltzmann distribution over the top, and then I tune the temperature, which is the free parameter of the distribution, to match the temperature of the gas, and you see that we get a reasonably good fit. So where does this distribution come from? It's a maximum entropy, maximum disorder probability distribution with a fixed average energy. So here we have the entropy of a probability distribution, and then we introduce a Lagrange multiplier to make sure it's normalized, and another one to make sure that the average energy is fixed. You find the probability distribution associated with these conditions by maximizing the entropy, and then you get something that looks like this. And I will say also that temperature can be given by the equipartition theorem. If that means anything to you, basically the total energy of the system, which is entirely the kinetic energy of the particles. The only energy in the system is kinetic energy, is proportional to the temperature and the number of particles. Is this clear? I mean, this is pretty basic. If you've taken a StatMech class, this will be very familiar. Okay, next question that we might want to ask is, so that's the details of the velocities. What is happening in the spatial structure of a system like this? So that's what we're going to talk about in this figure on the left. And the way that you do this in a sentence is you make a histogram of all pairwise distances between particles. So if you look in the inset, we have sort of a familiar frame for one of those movies that I showed you on previous slides. But now what I've done is I've drawn particular attention to this particle here, and now I'm just going to calculate the distance to all other particles in the gas. That's what these little lines are. And then I'm going to, obviously this is just for one particle, but you can imagine doing it for all n times n minus 1 over 2 pairs of particles in this box. That'll give you some big set of interparticle distances, and then I will make a histogram of these things suitably normalized. Okay, and that's what's going to be depicted in this figure here. That's this function g of r. It's known as the pair correlation function, or also known as the radial distribution function. There's a Wolfram language function called pair correlation g, which allows you to calculate this. And this is how you interpret this thing. A value of 1 corresponds to perfect spatial randomness. So if you just have a uniform distribution of points in your box, then you expect this to correspond to g of r equals 1. And that means that g of r greater than 1 means you're more likely than pure randomness to find two particles separated by a distance r, and g of r less than 1 means you're less likely than pure randomness to find two particles separated by a distance r, okay? So relevant features of these curves right off the bat, we expect them to be identically 0 up to 2 radii, because you cannot have spheres that are overlapping. You see that these curves are in fact not identically 0 because I did not use very much data, and I used some sort of binning function or something like this. So this is an artifact. And if you had an accurate version of these curves, it would be identically 0 out to precisely 2. And then we notice a number of interesting things here, but just to give you a little bit more data, this phi here is the density. So for hard sphere systems, you can introduce something called the packing fraction, which is the density, but you can express it as just what fraction of space is occupied by the spheres, okay? So the red curve is the lowest density, the blue curve is the higher density here. And we see that as you increase the density, this value at the point of contact starts to increase more and more. And this is interesting because, again, g of r greater than 1 means you're more likely than pure randomness to find two particles separated by precisely 2 radii. And what that means is that you have much higher than pure random chance to find two spheres touching in systems at increasing density, which points to there being an effective attractive interaction that emerges between the spheres, although the potential itself is purely repulsive. And this comes about due to entropy, which I'll explain on the next slide. But I'll also just say that if you have this curve here, this g of r, you can use it to calculate the pressure as a function of density. And the pressure as a function of density is known as the equation of state. And that's like a fundamental way of characterizing materials, basically. And it's one of the primary quantities that people care about when studying these systems. Okay, I mean, I'm just going over basics here, but you can use this function g of r to study spatial structure.
So these plots are for a specific time step, like a static image of the evolution of the system?
No, typically they can be, but your statistics will be pretty low. So what you do is you have a bunch of frames, you time evolve the system, and then you take the histogram of pairwise distances from this frame, this frame, this frame, this frame, this frame, you aggregate them all together. So this is like a statistical description of what the structure of your gas or liquid or fluid is like at equilibrium, or solid as well. You can do this for solids too. So yeah, you want to bin, especially if you want to do this with high accuracy, you want as much data as you can. Obviously, if the system is out of equilibrium and it starts with all the particles over here, and then a little later they're all spread out or something like this, then you're going to be conflating two different kinds of stories, and it's not going to be as good. But if you want to just describe equilibrium structure, this is a good way to do it. Yeah. And just a remark on the origin of this attractive interaction, you can basically think about it as coming from a kind of asymmetry. There are more ways for if we consider these two particles as being embedded in a sea of other particles that are bouncing around randomly, you have this kind of asymmetry where there's more ways for them to be knocked close towards one another and comparatively fewer ways for them to be knocked apart. So this asymmetry will mean you're much more likely than pure randomness to have spheres touching. And by the way, I didn't make this remark. This then dips below 1 quite substantially. So you're very likely to have spheres precisely touching when just viewed at random, and then that necessarily means that you can't have another sphere separated by 3 radii because it would be inside the sphere. This is a terrible explanation. If you just look at these two spheres here in this diagram, they're separated by precisely 2 radii. If you imagine trying to add a third sphere here, you would have to put it all the way over here. And you couldn't have it, say, where the center is at the point where my cursor is, because then it would be overlapping with this sphere here. So that's why there's this dip and then another peak and so on, like this. Okay, just to give you a sense of how you can assess spatial structure. I'll now move on to talk about phase transitions if people don't have anything else to say. Okay, so the interesting thing about hard sphere systems is that they can be in a variety of phases. These phases are associated with a variety of phase transitions. So phase transition is a discontinuous change of a system in response to a small change of some control parameter. One of the simplest phase transitions is the liquid gas boiling / condensation transition, which is familiar from cooking dinner. These are analytical results due to van der Waals in the 1870s, I believe as part of his PhD research. And I'll tell you about them in a second. And I just want to say that they were crucial in establishing the existence of atoms and molecules, which was still contentious at the time. If you think about how far we've come since the 1870s, I mean, it's crazy. That was yesterday. And they were having these discussions about whether atoms actually exist. And having models which explicitly assume the existence of atoms and then were able to describe features of the real world was crucial in establishing that process. Before we go into this, I just want to draw attention to this bullet point here, which is kind of interesting. Van der Waals is going to be hard spheres plus a little bit of extra business. And since we're going to be talking about hard spheres for the rest of the talk, I just want to dwell on how wrong the hard sphere model is if we take our modern understanding of nature. So the idea is that, we have an atom or a molecule and it behaves roughly like a hard sphere. So if we take a modern, what's known about the size and mass of an atom, so cheating a little bit, if we use modern data and we say, okay, then an atom is a hard sphere with a known size of an atom and the known mass of an atom, and you ask, what is the maximum possible matter density you could have in the universe? It has to just be the densest atom you have arranged as densely as possible. And if you do this, you get something like 10 grams per centimeter cubed is your highest possible density for matter in the universe. And if you look at the known value for the density of a typical atomic nucleus, you're off by a factor of 10 trillion. So this is really quite a radical departure from the from the atom as hard sphere view of the universe, I guess is what I'm trying to say.
Well,
Nevertheless, there's value to this approach, but still.
I mean, that's the difference between you're packing atoms at their electron orbital shells, and then as opposed to you're packing nuclei with protons and neutrons. That's
right. I mean, of course, this is silly, but this is fundamentally this. Okay, I mean, it's my understanding that fundamentally this is where we started, is do atoms exist or do they not exist? Do we have a continuum view of matter? Do we have like an atomic discrete view of matter? If we have an atomic view of matter, the place where that was basically started is the hard sphere model. And like it can calculate a lot of aspects of the real world, but it's like super wrong also. I mean, as everybody knows, but still it's fun to sort of dwell on precisely how wrong it gets certain questions. Anyway, let's talk about van der Waals. So what we have here is we have a pair potential precisely of the kind that we were considering before. Out at some distance r0, the potential becomes infinite. So it's a hard sphere at sufficiently close distances. Excuse me. But then we have this additional 1/r⁶ style attractive interaction. Excuse me, which you can argue comes about from dipole-dipole interactions. It's known as a van der Waals force. And it looks qualitatively like this. So one of van der Waals' contributions here was to figure out the equation of state of this system. So just so everybody starts at the same place, ideal gas law, PV over NKT is 1. This is what we learned in high school. N is the number of atoms in your system. And the equation of state for this system looks very similar to this. So the pressure is on the left-hand side, and we have NKT over V, which is the ideal gas law, but we have some reduction in the denominator here, and then we have a second term. And we see that the second term comes about because of the attractive interaction. And the effect of this first term is it looks like an ideal gas, but the denominator is slightly decreased, which means that the pressure is slightly increased. And that's due to basically the fact that you expect to have more pressure when these molecules take up more space. So what happens if you have an equation of state like this? So here we have the pressure of the system as a function of the volume of the system. You can also think of this as 1 over the density. And we see that for high temperatures, we just have a monotonic curve. But as we lower the temperature, this curve develops a non-monotonicity. The pressure is a function of volume. And you can calculate the equilibrium volumes of the system, or equivalently the equilibrium densities of the system at a given pressure. And we get these 3 points here. And it was sort of a great observation of van der Waals that these will correspond to familiar states of matter. So let me just remind myself what my notes say here. Right, so as we lower the temperature, we get a non-monotonicity. Right, so this means that the system can exist in multiple equilibrium states at a low enough temperature. If we take a look at this point here, if we compress the system, which means we lower the volume, we see a dramatic rise in the pressure as a result. And if we go over to this point here, if we compress the system, we get a very gradual rise in the pressure. Now, if we look at this intermediate point, we compress the system and the pressure actually drops. So that's an indication that this middle point here is going to be an unstable and therefore unphysical point. The point on the left, the equilibrium point on the left, is a liquid because it is recognized by the fact that it is very difficult to compress the liquid, and this is going to be a gas state here. So it was his great observation that these 2 points will correspond to liquid and gas phases. Right, these 2 phases can coexist in sort of like a bubbling kind of transition, which will also be familiar from cooking dinner. Okay, so I'm now going to talk about the specific phase diagram of hard spheres. So I'm introducing this basically as a model for phase transitions. We're going to now talk about hard spheres where the story is slightly different because there's no attractive interaction, and that will change things. But there are phase transitions, and I just wanted us to have this as a point of reference. Hard sphere equation of state, and okay. Are people still awake? Is this engaging enough? Because if it's going too slow, I can go faster. It's like I said, we have to sort of balance introductory material with new material, and your input is valued in that sense. But okay, so I'll just continue unless somebody stops me. So this is the equation of state for hard sphere systems. So on the horizontal axis, we have the density, which is equivalent to the volume fraction. As I said, what fraction of space is taken up by the spheres? If the spheres have no size, then they take up 0% of space. So the left limit of this is 0. It turns out that the right limit of this axis is approximately 0.74. This corresponds to a face-centered cubic sphere packing. You can't pack spheres any more densely than them occupying 74-ish% of space in 3D. The number obviously depends on the spatial dimension. Okay, so now we're going to ask what happens to the pressure as we interpolate between these 2 values, and we get the hard sphere phase diagram. So starting at low densities, it's sort of unsurprising. We start with an ideal gas at volume fraction 0, and then as we increase the density, the pressure increases as the spheres start to take up more of space. Once we reach a packing fraction of 0.494, we get what's called a freezing melting first order phase transition. If we approach from the left, it's freezing. If we approach from the right, which is say we start in a solid and we decrease the density of the system, then we get a melting transition. So we freeze at a certain point, so the pressure will remain constant as the density increases. And then at a certain point, we're following just the black curve here for the moment. This is the thermodynamic ground state branch of the system. We enter a solid phase, so here the states will be crystals, and then as we increase the density to a perfectly regular face-centered cubic crystal, the pressure will diverge. So for an actual system, you'll never quite get there. Just a brief remark about what is precisely happening between these 2 points. It's understood that in the thermodynamic limit, so if you actually had an infinite system, you could get this kind of bubbling transition where at this point you have totally liquid state here, and then you start to nucleate little bubbles of solid material. And as you move along here, the solid bubbles will start to take up more space. And then over here, you might have mostly solid with a few liquid bubbles. And then once you exit this coexistence region, you have a pure crystalline solid. So this is basically the state of affairs on the ground state branch. And then we have these additional curves here, where don't take the labels too seriously here. But the idea is it's possible to sort of continue liquid-like states of the system if you prepare it in just the right way. Specifically, what you do is rather than okay, so you have to imagine you get there from somewhere. So we start with an ideal gas and maybe we inflate the radii of the spheres or something like this until we hit a certain density. The way that you get states like this, which is equivalent to starting with spheres of a fixed size and like really rapidly crunching your box or something like this. So it doesn't have time to have everybody nicely rearrange themselves into a perfect crystal state or something, but it's trapped in a metastable state. So these states here are prepared in this manner by rapid compression of the system. And then at a certain point, you start to see things like maybe it's a liquid state for a while, but if you rapidly compress it to sufficiently high density, then it might start to take on glass-like features. And we'll talk specifically about what that means, but basically, you can think about it as how long would it take for it to relax to the crystal at the same density? And the answer is that it takes an arbitrarily long amount of time. And I'll show very precise numerical results saying like, yeah, it takes like an astronomically long amount of simulation time or something for it to relax. But this is the state of affairs. And I'll just make a point that hard spheres do not form liquids. So this particular van der Waals phase transition here, the liquid state was dependent upon having an attractive interaction. Hard spheres do not have an attractive interaction, despite the discussion of like an effective attraction. It's insufficient. So the low density state is variously described as a liquid or a fluid or a gas. They all mean the same thing. Okay, so this is the lay of the land. And it tells you that the single control parameter that we have, or I guess we have two, one is the density of the system, and the other is, are we rapidly compressing the thing, or are we letting it sort of find its true ground state? Okay. So a bit of a comment about simulation techniques. Oh, somebody is asking a question. Maybe I missed the comment, but right. Sorry, I missed this. This is a good question. So the question is about what is this vertical line here? So this limit is actually, this is a question of modern mathematical inquiry and a contentious topic. In the paper, I took a particular stance on this and was quickly contacted by somebody who has a different stance on this particular problem. So this limit here, FCC stands for face-centered cubic, which is a particular regular lattice. RCP stands for random close packing. So there's a conjecture here, which is that there's a maximum density associated with random sphere packing. So at a certain point, you just cannot create a random sphere packing of a density that's higher than approximately 0.64-ish. And I will say that this is a contentious topic, but you imagine that if you reach this random close packing limit, your pressure will also diverge because the spheres literally have nowhere to go. It's the densest possible packing, so the collision rate will diverge, and therefore the pressure will diverge. Gary, does this answer your question? Great. Okay. So we're about to start getting into actual results. I hope everybody's still awake. Thank you all for participating. How do you simulate these things? There are basically two ways. I mean, there's a huge literature. This is a 150-year-old topic that people have been more or less continuously publishing about. So there's a lot of things that people have had to say. But for simulating, there are basically two techniques. So there's the Monte Carlo approach. And the Monte Carlo approach is very simple. You have your spheres, they're sitting in a box. You move one of them randomly, and provided that it does not overlap with another sphere, you accept that, and now you have a new state of your system. If it does overlap with the sphere, you reject that move, and then you move it a different way, or you move another one, and so on. There are certain advantages to this approach. You can put it on a GPU and you can parallelize in a variety of ways if you're scientific computing kinds of people and you care about this. So sometimes you need to simulate enormous systems of hard spheres. And being able to put anything on a GPU that you can be very helpful. However, it can only be used to study equilibrium states of the system because obviously if you are moving particles randomly, they're not following their Newtonian trajectories. And I'm going to look at the chat for a second. If the pressure diverges at RCP, does the pressure just not mean anything between that and FCC? Right. So you have to think about following these curves continuously as a function of this density parameter. So people are sort of asking, like, my interpretation of this question is like, why can't I just like hop to the right from this branch here or something like this? But I think the way you should think about this is you start with a low density system, and then you actively have to prepare the system in some other state in the diagram. So you think about, you increase the radius of the sphere, or you compress the system, and it continuously follows either this curve to the FCC pressure divergence, or you compress it really quick and it continuously follows this curve, and maybe it has some sort of glass transition, something like this. That's also a famously subtle question. But thinking about the curves jumping to the right from this RCP to FCC, I think it's not the right way to think about it. What is possible in principle is jumping vertically. So the system has the same total density, but you get a total collective structural rearrangement of the system. So I can be more specific. If you have this point here, you have something that looks very much like a liquid. We have spatial disorder. If you look at the arrangement of the particles, and we'll show pictures of this later in the talk, they're totally random. If you look at the analogous point on the lower curve, the ground state branch, it will look like a crystal. So what you could have is you could have a spontaneous crystallization where somehow the particles swim around one another in just the right way that it finds a crystal state, the entropy is higher, and it will jump discontinuously from this top branch to this bottom branch. In practice, you generally don't find things like that. The time scale associated with such transitions is very long. I see people commenting, I'm curious how this would play out for hard spheres in 4D. Yeah, this is papers have been written on precisely this topic. Just because you brought it up, it turns out it is easier to have glassy states in 4 dimensions than 3 dimensions. In 3 dimensions, apparently, the statement in the literature is that these systems cannot help but crystallize in 3 dimensions, and it's much harder to get glasses in 3 dimensions. My experience was I had to work extraordinarily hard to get crystal states in 3 dimensions. But as you go to higher and higher dimensions, glassy states are more likely to be the outcome. And in fact, there is a sort of a tradition, or not a tradition, but a very active topic of study in the literature today is taking the spatial dimension to infinity. And you can do certain analytical mean field theory kinds of calculations in d equals infinity, specifically about glasses. I have references in the very last slide if you care about that particular line of inquiry, but you're not the first person to ask that question. It's a good question. And I see one more thing in the chat here. Okay, so it's a matter of whether we're actually quasi-static or not, I guess. Yeah. So the full story of what non-equilibrium means, I will explain. But yes, you should think about the compression rate. This is a specific parameter. So the way that we actually do it in practice, there's something called the Lubachevsky-Stillinger procedure, which is a fancy name for this thing where you start with particles with 0 size, you grow the radii linearly as a function of time until you hit the desired density. And then there's a parameter associated with that, which is how fast is the radius of the sphere growing. So this question of whether it's quasi-static, you want to grow the radius really, really slowly. And if you grow it really slowly, then you end up on this ground state branch here, this black curve. And one thing that I learned is that it is remarkably slow. You have to use a value of 10 to the minus 5 or lower for this parameter in order to get crystallization. If you go anything above that, you're going to get trapped on this metastable branch. So yes, yeah. These are fantastic questions. Okay. So Monte Carlo, you move spheres randomly, you can put it on a GPU. It's not what we're going to do. We're going to do molecular dynamics. So what that means is it's the same thing as what I showed you with those movies. The particles will move on linear trajectories, they'll collide, and then they'll bounce off one another. So this is fundamentally sort of a different kind of approach. The particular dynamics of the collisions are dictated by momentum and energy conservation. The particular rule is in the top right corner, and I'll just say this in detail here. So what you do is the particles move along straight lines, and then at a certain point they touch one another. And then you decompose the velocities into components that are along the axis connecting the centers of the spheres and perpendicular to that axis. Perpendicular to that axis, the component is unchanged. So v1 prime and v2 prime are the velocities after the collision. And we see the perpendicular component is the same as it is before, but the parallel component, so the component along this axis, is exchanged. So that's really complicated. Let's make it very concrete. I have a particle sitting at the origin, a hard sphere sitting at the origin. Another equal mass hard sphere comes along and bumps into it. What happens? So we follow this rule. We decompose the velocity into components that are perpendicular to the line connecting the centers of the spheres and parallel. Obviously, all of the velocity is on the line parallel to the centers of the spheres. So we exchange the velocity components along that line. So what happens, this particle comes along, it bounces into this particle, it stays completely still, and then the particle next to it moves on. And this would be familiar from like playing pool or something like this. Is that clear what I'm saying, that simplified picture? The other limiting case is if you have a totally glancing collision. So obviously the particles are just going to move right past one another. But we can apply this rule and make sure that it gives us exactly what we expect. So at the moment that they glance, you decompose the velocities into parallel, so along this axis and along the horizontal axis here. And along the axis connecting the centers, you exchange the velocities, but the component is zero there. So that doesn't change. And then along the perpendicular component, it doesn't change. So we indeed reproduce this glancing collision dynamics where nothing happens. Okay, and the point of this formula is that this allows you to interpolate between those two cases. So if you have some finite impact parameter thing, they bounce off one another. This is the rule that you always end up following, which comes from momentum and energy conservation. If you do molecular dynamics, you can use certain data structures to accelerate this, like binary search trees, if you're computer science people and care about these things. The advantage to this approach is that you can drive the system out of equilibrium, and this simulation technique will allow you to explore non-equilibrium physics as well as equilibrium physics, whereas the Monte Carlo approach is just for equilibrium kinds of calculations. And whatever, these are implementation details. You can calculate precisely the time at which the collision occurs and use that to speed things up and so on. Are there questions?
Can I ask a question?
Please, yeah.
When I took an advanced computational physics class, we created this Maxwell distribution. We generated this Maxwell distribution curve by simulating these collisions between finite number of particles, but we used the Leonard-Jones potential instead of the step function like you mentioned. And we considered the forces from all the other particles on one particular particle. But from what you just said, it seems to me like only two touching particles are involved in the velocity change in velocity.
Correct. That's right.
So what if there are other particles, hard spheres, also bouncing on other? I mean, more than two are involved.
So that's a great question, and the answer is that as long as you do not have a perfectly symmetrical initial condition, and I'll say what I mean by that, those kinds of collisions actually do not occur. It's like a probability zero kind of thing. So here's a counterexample to that. I have a sphere sitting at the origin, and I have two particles symmetrically around it. They move in at exactly the same time, and they sort of symmetrically crunch this central particle, and then they bounce off. They do whatever they're doing. That kind of situation, in principle, can certainly happen. However, if you imagine displacing one of these particles by however small you want, by epsilon, it can be arbitrarily small, then the fact that these hard sphere collisions are instantaneous in time means that you actually will never have a three particle collision of precisely that type. So it's like a probability zero, measure zero kind of phenomenon. And in practice, so you could get into trouble if you have a finite time resolution for your steps. So my simulation has a dt of 0.1, and this particle collision is like 10 to the minus 6 before this other one. Then I can get some sort of simultaneous collision weirdness. And I mentioned that the hard sphere simulation function on the function repository is slightly less sophisticated. It can have situations like this because it uses a fixed dt, a fixed time step. But in the algorithms that we use for the paper, you calculate the time precisely, like as many digits as your computer will give you. We use 16 digits. So that means that you never get these symmetrical three-body collisions or things like this. The reason why you get them for Leonard-Jones is because in principle, the Leonard-Jones potential, for those people who don't know, Leonard-Jones looks like it has very strong repulsion at short distances. It has an attraction at slightly longer distances, and then it asymptotically goes to zero. But in principle, it's slightly non-zero all the way out to infinity, so you have to sort of calculate the effect of many particles at once. And it's a very specific thing to the hard sphere problem that you don't have to consider situations like that, as long as you don't have symmetry in your initial conditions. And since we make our initial conditions through this like dynamical growing procedure that I talked about, there's no symmetry there.
Okay, thanks.
Yeah, you're welcome. Good question. Okay, so you guys want to finally talk about the results of this paper? I told you we were going to go from 0 to the results of the paper, so we had a long way to go. Okay, we haven't talked about the Wolfram Physics project almost at all. This is I hope I've convinced you that there's good reason to look at these systems. Now what we're going to do is we're going to introduce a network type construction, a graph theoretic kind of construction in the context of hard sphere systems, and see if this gives us anything. So I've told you what our simulations are going to be, and now we're going to sort of add some machinery on top of this. So broadly speaking, network constructions can be used to infer global structure of systems, very generally stated, composed of many interacting components. So that fits the description of our problem. We've been talking about, like, what if you look at the velocity distribution? What if you look at these pairwise histograms? These are fundamentally functions on phase space, statistical functions of phase space quantities that typically we use in statistical physics to try to make sense of the structure of these systems. We're now going to talk about something very different, which is a network style metric, and see if this gets us anywhere. So there are three obvious candidates for such network constructions, although by no means is this exhaustive. You can do all sorts of other things. The first one is something called a contact network, and that's what's depicted in the top right corner here. So this is some bidispersed system that I took from some paper, which is cited at the bottom here. We have spheres of two different sizes. They're arranged in the box and they're all touching one another. Excuse me, or many of them are touching one another. And what you do is if the two spheres are touching, you just draw a line connecting the centers of the spheres. So the nodes will sit at the centers of the spheres and the edges will connect them if they are, if the spheres are touching. And then you can imagine, all right, forget about the spheres now. I can take them, I can throw them away. And this leaves me with just an abstract sort of network. And this is extremely widely used in the hard sphere literature. Specifically, it comes up in the context of the jamming transition and jamming studies, which is one place where there's a lot of interesting physics in these systems. Now, it's suitable for static calculations, but not for dynamical calculations. It's not really clear what you would do for a dynamic version of this kind of calculation, but you can use this by looking at, for example, the node degree distribution, so the probability distribution of the node degree on this network. You can infer things about the spatial structure of these kinds of systems. So this is one approach, and we're not inventing this. Another approach, which in principle we are inventing, but the value of this is not clear, is the second thing that I've defined at the bottom, which I'm calling in quotes a collision network, but it should not be, maybe you'll have a better name for this. So what we do is we're interested in dynamical aspects of these systems. So obviously a hard sphere simulation like this is just characterized by a sequence of collisions. So what we do for this kind of network construction is a collision is some ordered pair ij for particle I and particle j. We construct all possible ordered pairs, and then we arrange them on the edge of a circle. And then we can think about the dynamical evolution of this hard sphere system as just jumping from collision to collision to collision to collision. And this will manifest itself as a directed walk on this graph. So this is another way that we could do this, but we've thrown away a lot of information in this construction. In particular, we have no information about the spatial relationship between the particles, which the contact network certainly gives us. We can now track dynamics, but we've thrown away so much that I'm actually not certain that there is a use for this kind of construction. It's sort of close, but I mean, one study that you could imagine doing would be preparing some non-equilibrium situation and then following the walk on this graph and sort of trying to see if you can quantify when it approaches equilibrium or something like this. I think somebody had a question, maybe.
Excuse me.
Yeah, please.
Yeah. Could you please explain what this top right picture is showing exactly? There are dark circles and
Yeah, so I don't know what the
shaded
dark circles
circles.
are. So I was just using this an example of a contact network. So I should have read this paper more carefully, but I just have it here as an illustrative example. So if you forget about the dark circles and the shaded circles, we just have circles, and there are two radii here. It's called a bidisperse system. This is another sort of control parameter that you can use to make interesting things happen. I wonder if I can zoom on this slide. Yeah, so forgetting about the meaning of the dark circles and the shaded circles, the only thing that I wanted to draw your attention to is that you can make a construction like this where you have some disordered arrangement of particles in space, or maybe it's an ordered arrangement of particles in space, and you use the fact that two particles are touching to create an edge between them, and then the vertex in graph theory language will now sit at the center of these particles. And then you can imagine, once I've done this and I've constructed my network, now I forget about the particles and I just do graph theory on the underlying network structure here. That's all that I wanted to say about this.
Okay. Thank you.
Yeah, you're welcome. Okay, so we want to sort of come up with sort of a hybrid approach between these two things, and that's what the causal graph is. So now we're finally going to connect to the physics project. This was Stephen's summer school suggestion for me in 2020, was basically construct a causal graph for a hard sphere system. And the causal graph is sort of a hybrid approach between these two kinds of things. So I have here, this is stolen from Stephen's purple book. This is just an example of a causal graph. And in fact, this is a much more complicated kind of causal graph than the kind that we will encounter in this study. So this is a string rewriting system. We start with some initial state, ABA. We have some substitution rules. Then we apply the substitution rules in all possible ways. We get this big multi-way system where the states, which is to say the strings themselves, are represented in these blue squares, and then the updating events are represented in these orange squares. And then what you can do is you can say, you can sort of connect the updating events themselves by causal relationships. So this updating event happened, and then it created some states which were subsequently updated. So those states or those updating events are causally connected with one another. And then you end up with a set of relationships just among the updating rules themselves, and you get this complicated multi-graph kind of thing, directed graph. And in fact, this is more complicated than the kinds of causal graphs that we'll consider in the context of hard sphere studies. So we'll start with a very simple simulation, if I can get it to play. Something like this, okay? So we have, this is the equivalent of like a Newton's cradle with periodic boundary conditions or something like this. And what I'm going to tell you is that we can construct this particular directed acyclic graph from that evolution. It'll just take a moment for us to internalize the particular rule, and then we'll go forward and we'll try to use this to do physics. This is what the paper is about, by the way, is taking this causal graph construction and then applying it to some interesting physics scenario. So what is the rule? We take our list of collisions, we run a full hard sphere simulation. So we're propagating the positions and velocities as a function of time. The end result of that simulation is we have a list of collisions. The collisions look like an ordered triple like this. So there's two particles involved, that's particle I and particle J, and then they collide at some time t0. We're going to construct a network from this according to the following rule. Take all of the collisions that involve particle 1, so where either the first argument or the second argument is 1, and then arrange them in a time-ordered list, and then just connect adjacent ones by directed edges, okay? So that's what this bullet point here is saying. This collision involves particle I and particle J. This collision involves particle K and particle I. They both involve I, so we're going to connect them by a directed edge, okay? So if I have 3 of them. First, we have the collision at t0, then t1, then t2. All of these things involve particle I, so we'll connect them in a row by directed edges. Okay, so in some sense, this is an arbitrary rule, and note that it's not transitive, you just connect adjacent ones. And the question that we have to ask ourselves is, does this construction offer any physical insight? So it's always tough to introduce this because they just sort of have to assert it out of the blue. So it's a little bit more helpful to color the graph just for the moment to give you a sense of the intuition. So this is exactly the same graph as we were looking at on the previous page here, but now it's colored. So like I said, give me all collisions associated with particle 1, set them in order, and then connect them with adjacent edges. That is going to correspond to, that means that the edges in that particular subgraph will all correspond to the same particle. Now give me all the collisions associated with particle 2, connect them by directed edges. That means all those edges will be associated with particle 2 and so on. So what I've done here is I've colored this graph according to the particle that the specific edge corresponds to. So we start here with a collision between particle 1 and particle 2. And then what happens? We have particle 2 collides with particle 3, 3 collides with 4, and so on. This is the Newton's cradle evolution. But it's sort of easier to make sense of this by following the edges of a specific color. So particle 1 collides with particle 2, and then the collisions move on down the line, and then eventually 5 wraps around and collides with 1. So that's what this node is. And then 1 collides with 2, then 5 collides with 1, and so on. So you can imagine following this particular blue set of edges through the graph, and you can retrace the history of what particle 1 in particular does. Now, instead, I can follow particle 2, which is the red edges. So 1 collides with 2, 2 collides with 3, and then the collisions wrap around, and then eventually 1 collides with 2 again, 2 collides with 3, and so on. So you see, we can decompose the graph into these directed path graphs like this, and they sort of stitch together to form this object.
Quick
Go ahead.
question on the times. Does the after comma digit mean anything specific? Because it seems to increase from like 1, 2 to 3 and 4. Like 2.1.
So the time is the third coordinate here. It's just the global simulation time of this thing here. So I guess the first simulation happens at time 2.1. Excuse me, the first collision happens at time 2.1, and then I guess it takes like precisely 2 time units for this collision to be followed by this collision. So that's why it's 4.1.
So it's just random that like the after comma digit keeps increasing from 1 to 2 to 3 to 4.
Oh yeah, that's that. There's some, I just put these regularly spaced in a box of a certain size. Yeah, I wouldn't attribute any significance to it. The real sort of significance is the connectivity and the fact that we have the times at all, if that helps. Okay, so this is the construction. And this is always like the toughest part of the talk because it is an arbitrary construction. But just thinking back to these other graphs that we introduced, this gives us spatial structure, but we can't do dynamical calculations with it. This gives us dynamics, but it throws away spatial structure. It throws away so much that I'm not convinced that it has value at all. So this is sort of a hybrid approach where we don't have spatial structure, but we do have this particle identity information because the collisions are labeled by the particle identities. We also have time information. So we have these paths which have meaning, and then there's a question of, can we get more meaning from the global connectivity structure of the graph? And that's what I'm going to continue to talk about. But I see that Saul has a question, so go ahead.
Yes. What's the meaning of the last member of the list, Matt?
It's the simulation time where the collision occurs. So in some sense, I should have like this should have been 0, right? So the first collision happens at t = 0, but I guess from the simulation time perspective, it took 2.1 time units for the first collision to occur.
Okay, thank you.
Does that help? Yeah, you're welcome.
So if you took the movie of what happens to the particles and you colored the particles, and then you played that movie downward in time, like you saw the film strip, I guess it would you'd have like an analogous.
It's analogous, but this thing should not really be thought of like that's sort of a space-time diagram kind of perspective.
Sure, yeah.
This is not a space-time diagram. Like the particle is not turning around and curving around. Like we're in some sense want to do as much with pure connectivity information as we can. So,
but this you would have a mapping from that combinatorial, from that structure, from that movie, I guess, to this combinatorial structure.
Yeah, that's right. So ideally what we want to do is we want to get away as much as we possibly can with like pure topological information about this graph itself. We'll have to use a little bit more. It's not like these contact networks where you can just do pure graph theory. Like we're going to use a little bit more information, specifically the node labels, will come in a rather crucial way, which is sort of equivalent to saying we'll use the colored edges, like we have the edges colored in this plot. That information we will use for the purpose of this study. But I think people sort of have a rough sense of what this thing is. So let's talk about some advantages to this approach. So the first advantage is that the graph is invariant under a large group of transformations to the underlying system. So I can take the system, I can translate it in space, I can rotate, I can reflect about the origin, I can time translate, I can Galilean boost. I'll get exactly the same causal graph on the other end, which is just a basic consequence of Newton's laws of motion. So if I can calculate certain things from the causal graph, then I will be able to say them regardless of, all of these various underlying transformations to the system. And those quantities won't depend on any of those transformations. Mathematically, the in degree and out degree of each non-boundary node is 2. So there will be, this top node doesn't have an in degree of 2, but if you have like a very long causal graph like this, basically every node will have in degree and out degree 2. It's a directed acyclic graph. It's not necessarily connected, but it typically is, as long as you run the simulation for a sufficiently long amount of time. And every collision adds a new node to the graph, which is the difference between this sort of collision network that we were looking at a few slides ago and this one. And that means that if I have an infinite system or I run for an infinite amount of time, I will produce an infinite graph. From a practical implementation perspective, for the study that we did for this paper, sometimes we have simulations that have 500 million collisions or something like this for reasons that we can talk about. And that means that we have a graph with 500 million nodes and 1 billion edges. And you sort of run into interesting implementation questions where, using the Wolfram language out of the box graph theory machinery, you start to have to wait a very long time. So we wrote our own for certain aspects of the study. Anyway, that's just sort of neither here nor there. I don't know how many people care about implementation. It's probably a mixture in the crowd. So the question is, how can we use the causal graph to do physics? There are basically 2 quantities to look at. There are paths, and there are these so-called out components, which I'll define on the next slide. Out component is a network theory term. So the paths are associated with individual particles, like I said. And those were the colored edges in the graphs that we looked at a little while ago. So we can obviously use that to extract a collision rate because we have a sequence of collisions with associated times, collision rate for each particle. If you want to sort of divorce yourself from using the node information, you can think about this. We have some big complicated mess of a causal graph, and I'm establishing a foliation of the causal graph, and then my collision rate can be extracted by counting the number of nodes inside a foliation. But personally, I'm not inclined toward that perspective. I'm just going to use the node label information to calculate a collision rate. And for those of you who care, there's a way to extract the equation of state directly from the collision rate. The collision rate is gamma here. So PV over NKT is 1. That's the ideal gas law. There's a correction term, which is linear in the collision rate. So as we have a finite size for our spheres, there's a finite collision rate in the box. This will give us the equation of state, excuse me. So we can use the collision rate, and therefore, in sort of an extended way, we can use these single particle paths to calculate the equilibrium physics of the system through this equation of state. But you can also use the collision rate to in some totally non-equilibrium scenario. And maybe this formula won't hold anymore, but you can still calculate the collision rate and use it. Another thing that you can do, because remember our nodes are labeled by this triple of information. So if I look at a single one of these paths at the time, the blue path, I see in this case that I can look at the total number of other particles that this given path, this given particle is going to collide with as a function of time. So let me be more concrete. Imagine I have 2 particles fixed in space and my Hart sphere is just bouncing back and forth between them. Then the relevant number is 2. So there will be some path through the causal graph, which is the sequence of collisions, but I see it's only colliding with this guy and this guy. So that number is going to be 2. And you can imagine in a different scenario where you have just like a totally mixing liquid and this particle goes off and it collides with every other particle in the box, then that number will be n-1. So these are sort of the 2 extremes. If I have an actual simulation, what number am I going to find suitably averaged over the system? So this is a way of using individual paths in the causal graph, but understandably, people might not be super happy with this because you're not really making use of the full connectivity structure of this graph. You're plucking out one path at a time, doing everything you can with that individual path, putting it back, plucking out another one, and then repeating. So ideally, we would also have some constructions that would make use of the full connectivity structure of the graph. So that's where this out component object comes in here. So if you look at this graph here, the thing highlighted in blue. Oh yeah, go ahead.
Before we move on, that was a lot of very interesting information. I did not grasp it.
Oh,
How did you come up with the foliation? You just counted the number of events, and then you just like a static number of events, and then you foliated after you reach that number.
Right. So okay. So yeah. Let me say this point again and slow down. So the first thing is if you don't like thinking about foliations, you never have to think about them. The foliation is I'm introducing as sort of like an equivalent way of defining the collision rate, which you can obviously define a collision rate if you just look at like a labeled version of this graph and you just look at the blue path through this graph. You have a collision at 2.1, 12.2, 14.2, whatever. Obviously from that you can calculate a collision rate. When we started this project, one of the sort of naive perspectives that unfortunately did not come to fruition was the hope was that we could just do topological kinds of constructions on this causal graph. Like it'll just be a question of whatever geodesics or calculating balls or something on this graph, and I could do all of the physics I wanted to do with that only in terms of such quantities. It turns out that this does not work. But one way that you could sort of move closer to that perspective, instead of actively using the labels on the nodes, is you could say, okay, suppose I have my causal graph. I'm now going to introduce a foliation corresponding to fixed time slices. So that's what these black lines are supposed to indicate. So this is t equals 0, say, and then this other one comes at t equals 1. So I'm going to arrange my nodes faithfully in time, but the spatial arrangement doesn't matter. And this is my foliation. And then for a given path, I will count how many collisions fall into this bin, how many collisions fall into this bin, and so on. And from there, I can also get a collision rate. And in some sense, it's more topological. It's more consistent with like I don't know, we're trying to introduce GR type thinking on these graph kinds of structures. If you're insistent on thinking like that, I personally, it's unnecessarily complicated, in my opinion.
And I guess that's also where I'm confused, as in the multi-rate graph before, we knew exactly each state was a collision and we just calculate number of collisions. But if the causal graph, we can jump states, right? Because we're looking at the events. At least that's the causal graph you showed before. So the number of causal events, like, it just seems like, how do I get back to a collision rate from there?
Right. So the events in this causal graph are indeed events. The events that you should think about is each node in this graph is a collision event. So maybe that helps to ground you. But it's exactly the same story as before. So let's just look at this graph here. By the foliation perspective, I mean, I'm going to arrange my nodes in, what is the best way to say this? I'm imagining sort of drawing horizontal lines and chopping this causal graph up into time bins. And then each of these time bins will have a certain number of nodes associated into that bin.
So this is a causal graph too, not just a state graph. So they coincide in this case.
This is the only kind of graph that we're going to talk about from here on out, and it is a causal graph.
Okay, thanks.
Are you confused? I'm sorry.
If you go back
more.
like a slide or two, remember like the causal graph you showed was
this thing, you mean?
Yeah, you can like here there was an annotate things, like where you can jump certain states, like this one in the causal graph, right? So I guess that's where I was like, okay, if this is a collision, but we jump it going like, from here to here in the causal graph, then like we're missing this collision. That's how I got confused.
It's possible that I should not have included this graph at all because it might be adding confusion. I don't think I super duper understand exactly how these I'm not sure I have a good answer to your question. The causal graphs that we're going to consider going forward are structures like this. The collisions are events in the sense of, excuse me, the nodes are events in the sense that they correspond to collisions. There are no states in this graph. So right, so these graphs here have hybrid. It has state and update rule associated. That's the blue and the orange squares. The causal graphs that we're going to consider are in a sense more analogous to this structure on the right. I said this was more complicated because it has things like self loops and multi-edges and things like this, which we won't have. So it's all events.
Got it. Thanks.
Thanks for asking questions. I'm sorry that I'm flying over this material in Xerxes. I'm well aware of how the time has brought us here. So we'll do a fast overview of the results of the paper, but you all have followed to this point, so you're well equipped to read the paper and understand what we've done in detail. But anyway, the other kind of structure that you can define is the out component here, which is this blue structure. You start at a given node, and then you follow all directed edges out from that node. And then every time those edges encounter a node, you follow all directed edges out of that node as well. So in some sense, you can think of this loosely as analogous to like a future light cone on this causal structure, if you like. But we decided to just keep the graph theoretic terminology because they're not precisely the same thing. And the idea is that we're going to okay, so now we're going to get to the actual like meat of the paper. We're going to do some simulations. We're going to take a hard sphere system. We're going to put it in some situation where it's going to do some physically interesting behavior. And then we're going to take these two tools and we're going to see how they allow us to learn things about the system. What I have in the bottom here is that we're going to see that the out component for some crystalline configuration like this is going to have very different behavior than some low density state like this here. Okay. Man, I don't think it's ever taken us this long to get to the results section. I'm just speaking directly to Xerxes now. Like I said, 2 hours is like an interesting amount of time because it allows us to do details, but okay. So what we're going to do fundamentally is we're going to prepare systems at various densities, and then we're going to time evolve them using the algorithms that we've seen, and we're going to look at equilibrium physics, and we're going to look at non-equilibrium physics. And unfortunately, I'm going to give you the 1,000-foot view of these results because we are having too much fun, and we have to make trade-offs somewhere. So the quantity that we're going to focus a lot on is this gamma of t here. This is the single particle collision rate. So you can forget about the causal graph. You can imagine just following one of these particles around, you calculate its collision rate. Alternatively, we can construct a causal graph and we can use these single particle paths. We get the same thing. That's this gamma of t. And then we're changing the density, which is this phi. And we see that as a function of time, for these systems that are prepared in equilibrium, this is just a constant with fluctuations. So this is what thermal equilibrium looks like. It's very boring. So what I can do is I can do the time average of these curves here. So this is exactly the same figure, and I'm just taking the average value over time at each density, and we get a curve that looks like this. So the reason why we care about the collision rate is it is related to the pressure by this like straightforward affine transformation. So if you like, you could just replace gamma with P for the pressure, and then that's exactly what we're looking at here. So and this is the equilibrium behavior of the system. I've put this coexistence interval where we expect a phase transition to occur. And that's these vertical dashed lines. So now we're using a high accuracy simulation, but it's doing basically the same thing as the function repository function. And we see that at a certain point, we get a non-monotonicity in the pressure versus density curve, which you might remember from the van der Waals discussion. This is suggestive of a phase transition, but we see that our system is fully crystallized. These are crystalline states up here at a slightly higher density than other people have reported in the literature. We can talk about why that might be the case, but in any case, this is the equilibrium physics of the hard sphere system summarized in a single plot: pressure versus density, like we discussed. Okay. So now what we're going to do is we're going to drive the system out of equilibrium. Don't focus too much on the slide. In fact, maybe don't even look at the content of the slide at all and just listen to what I'm going to say. We have a bunch of spheres in a box. We'll prepare them at equilibrium. And then what we'll do is we'll do the equivalent of like sticking a hot poker into the center of the box or something like this. So we'll take a spherical region in the center of the box. We'll give them way more kinetic energy than the surrounding material. So this is analogous to having a very hot core of maybe 5% of the particles and then very cold surroundings. But we'll prepare it at the same energy as these simulations that we were just looking at, and we'll see what happens. So if we do this, we get this kind of behavior of the collision rate, which again is basically the pressure as a function of time. At long times, we get some stabilization to some asymptotic value with small fluctuations consistent with equilibrium, but at short times, we get some sort of transient behavior where it starts low and then maybe it bounces around a little bit before stabilizing to its equilibrium value. And again, the color corresponds to the density. Our high density systems are at higher pressure. We get some sort of transient behavior. Okay, more or less clear what I'm saying? These are the non-equilibrium dynamics of the title of the talk from 100 hours ago when we started. So we can look at, so clearly it relaxes and returns to equilibrium, and clearly it is not in equilibrium at early times. So what we can do is we can plot these things right on top of one another. So this is some high density state, which is prepared by this sort of inflating procedure. We inflate the spheres very, very slowly. It forms this crystal here, and then we take the crystal, we time evolve it at equilibrium, we get this red curve, and then we do the equivalent of sticking a hot poker in the center of the thing. We heat up the central region, we allow it to sort of expand outward and slam into the rest of the material, and we get this blue curve here. So eventually it settles down and it lands basically right on top of these other curves, but there is some transient sort of behavior. So we want to be a little bit more quantitative about this, so we can do one better thing here. So what we'll do, and this is very consciously making use of the information that the causal graph allows us to, or the style of thinking that is motivated by the causal graph. So we have some system of spheres that looks like this. Some of the spheres start out with 10 times the velocity of in the center, they start out with 10 times the velocity as the surrounding particles. And what we'll do is we'll partition those into two groups, and then we'll look at the paths in the causal graph associated with the hot initial spherical region, and then the paths through the causal graph that are associated with the cold surrounding region, which looks like a sphere with a cube with a sphere sort of plucked out of the center. And then we'll follow those two paths as a function of time. Of course, the dynamical simulation is exactly the same as it always is. We're just initial position, initial velocity, time evolved the system as before. But once we have the causal graph, we can start to ask very specific questions, like what if I focus on this group of paths as opposed to this group of paths? So that's what we're doing here. So we divide the collision rate into these two populations, and then we take the difference. This is as a function of time. So let me tell you how to interpret this curve. Positive values of this curve mean that the particles that were initially in the center that were hot have a higher pressure, higher collision rate than particles in the surrounding area. A negative value of this curve means that the particles that are initially in the surrounding area have a higher collision rate at that time than the particles that were initially in the center. So it is unsurprising that these curves all start positive because the collision rate in the hot central region is expected to be high. But then what happens? You just by pure randomness of the motion, the particles are going to end up moving outward at very high velocity and colliding with cold material that's immediately surrounding them. And it's going to dump almost all of its kinetic energy into the cold surrounding material. And it's going to leave behind a cold spherical region in the center. And then this process is going to trade back and forth very quickly. So that's why these curves oscillate here. So the red curve is a high density liquid below the solidification sort of density. And the blue curve is a crystal state. So we see the kinetic energy starts in the center, it's rapidly distributed to the surroundings, and then they sort of ring back and forth until everybody's at the same temperature, everybody's at the same pressure, everybody's the same everything. And that's why this curve asymptotically goes to zero. I see I'm now at 3 o'clock Xerxes, so I will start doing the fast version of the pitch. There's more material here, everyone, and I encourage you to talk to me after or read the paper. And anyway, that's the situation that we're in. And the point being, so there's there's some sort of trading back and forth where the energy starts in the center, it's distributed to the edges, and maybe it bounces back and forth one or two times until everything basically equilibrates. We call this in the paper some sort of compression wave type phenomenon, and we see that there's a density dependence where the crystal ends up statistically at 0 faster than the solid. We can assign a time scale to this. The high density systems will relax much faster. This is the time scale, this is density, than the low density systems. It's a shame to fly over this material so fast, but again, I'll give you the 10,000 foot view now so that I want to be respectful of your time. We are now going to go to the metastable branch of the phase diagram. So instead of infinitesimally slowly, quasi-statically increasing the radii of these spheres, we're now going to like take a bike pump and just slam it. So they go from 0 radius to radius 1 in no time flat. That will put us on this metastable branch. You get some sort of spatially disordered configuration like this. And we look at the collision rate again. So what is the pressure as a function of time? It looks like this. If I rush through this and you don't have much time, you might say that it looks exactly the same, but with a slightly different behavior at early times. But if you plot them next to one another, again, we have time here, we have collision rate equivalent to pressure on the vertical axis, we see that the system prepared at thermal equilibrium are these red points. This is a high density phase. So this is basically the definition of a glassy state. And I'll basically stop here, I think. We see that the collision rate is dramatically higher for the glassy state, and it is decaying towards the equilibrium value. If you plot it in a log-log scale, you see that there's a power law decay to the collision rate as a function of time, but the power is something like 1 over t to the 0.06 or something like this. So you get this incredibly slow decay of the pressure in these metastable states back to the equilibrium value. If you extrapolate naively, you get a lifetime of 10 to the 9, something like this. You get these extremely long-lived states which deviate from equilibrium. And we have a whole story about this. Such a shame. There's a couple of good things to see here. These out components, if you visualize them growing as a function of space for a crystalline configuration, you see they grow these roughly spherical-ish structures, but they have little tendrils. And if you go down to the glassy states, they get much more tendrily and they grow much faster. So this is an indication that the spheres are really tightly pressed up against one another. And the purpose of this figure is to tell you that even though they're really tightly pressed up against one another, they're still somehow moving around. But I'm mindful that you guys have been in talks all day and I'm over time. So let me just summarize. The hard sphere causal graph, it provides a new perspective on hard sphere systems in the sense that it is complementary to phase space information. We're not throwing away any phase space information. We're just taking a different perspective, and it allows you to investigate certain things. And it motivates asking certain questions that otherwise might be somewhat unnatural to ask. Like, for example, if you look at the growth of collisions as a function of time, you get these nice spindly structures. That's precisely analogous to this out component, but asking that question in a vacuum might otherwise be sort of an unnatural question to answer, to ask. If you look at individual paths through the causal graph, it allows you to study relaxation behavior, as well as the equation of state at equilibrium, and you can also use it to quantify the degree of mixing, although I had to speed over that, so I didn't really explain that at all. These thermal inhomogeneities, where you heat up the center of the box and then allow the system to evolve, and it eventually returns to equilibrium, that happens very fast. At high densities, it takes like 2 time units. At low densities, it takes maybe 20 time units, but the order of magnitude here is somewhere between 1 and 10, where the higher density systems relax faster. In contrast, if you prepare a glassy state by really rapidly compressing the system to some high density disordered solid state, and then you allow it to evolve, the timescale associated with that returning to equilibrium is astronomically long by comparison. So this is what is basically meant by glassy systems. And glasses are an object of much study in the modern sort of hard spheres literature. And I have some references to that effect on the next slide. I had to rush over this point, so I won't say it, except to say that in these glassy states, there's some degree of rearrangement of the structure of the material. Right, so the message of this, one of the interesting lessons that we drew from this study, which is an extension of things that people have known for a long time, is that these glassy states have sort of a hybrid character where it's like half in equilibrium and half way out of equilibrium. So the pressure is way out of equilibrium, as we say. But for example, if you took one of these glassy states and you stick a hot poker in the center of it, again, this kind of thermal perturbation, that will relax very quickly, like much faster than it will in the crystalline state, because it's just determined by the total collision rate of the system. So possible extensions, maybe things for you guys to work on. You can apply this, you can extract a causal graph in other situations. You can put the hard spheres in some sort of external potential. Maybe the potential is changing as a function of time. You can apply it to this compression procedure itself. Perfectly well defined in that case. It might be the most straightforward extension. Add dissipation. You could try applying it to other hard particle systems. So for those of you who don't know, there are things you can use hard rods, hard ellipsoids, things like this, and that's very deeply connected with the field of liquid crystal physics, where there's lots of good stuff to learn. And I don't know much about it, but you could certainly apply these techniques there. And then applying the causal graph for continuous potentials like Leonard-Jones, like we talked about, or soft spheres or something like this. In principle, you could do this in quantum mechanics. Personally, I'm doubtful, but maybe you can prove me wrong. And I include these references here as examples of sophisticated modern treatments of the glass transition. And I want to point you in the direction of, like, in my opinion, the deepest physics in this area is being done on precisely the topic that these papers are about. This is a book, actually, this top one. With that, I will conclude. I'm sorry for going over time and for rushing, but I'm happy to take any questions if you have them. And thanks for listening.
Thank you, Matt. Let's thank the speaker, and we could take a bunch of questions.
I will stay for as long as people want to take questions. It's a shame that we didn't get to cover everything. I'm sorry. That's on me as the speaker. I should have been able to navigate that. All right. Anyone?
What were the dendrites for the liquid phase? Can you go back a couple slides?
Thanks for coming, John. These things, you mean?
Yeah.
So what this is this out component structure here is you start from a node on the graph, which corresponds to a single collision, and that's what the left frame is. And then the question is, as this out component grows as a function of time, or as a function of graph distance, alternatively, it's going to sort of swallow more particles as a function of time. And if you take this really far into the future, all of the particles will be included in this thing.
Sure. Oh, okay.
So the entire graph will
So-
be blue after a certain distance. So what I'm doing here is I have a full crystal in this case, and I have a full glass in this bottom case. And what I'm doing is I'm choosing a random collision near the center of the box, just for
I see,
visualization
I see.
purposes.
So
Yeah.
two collide, and then those collide into other things, and after 0.5 time or whatever, this is what it looks like.
That's right. So I'm just tracking everybody who's causally connected to this collision. That's what this is showing.
Okay. And for the glassy phase, it's glassy, I guess. I mean,
well, the reason why this is sort of valuable to see. Yeah, so it has amorphous spatial structure, and you can see this here. So this is exactly the same thing. I've just taken a late time frame for a big system. On the left, you have a crystal, and you can sort of see, if you look closely at this, and try to zoom in, you can sort of see the crystal axes a little bit. But if you look, by contrast, at the glassy system, there's no structure to be seen. But in fact, it's more than just the fact that there's no structure to be seen. The most efficient use of space is to have a regular sphere packing. That's just like a mathematical fact, basically. And these glassy phases geometrically correspond to disordered sphere packings. And what that means is that they're inefficiently using the space, and the spheres are locally going to be really sort of trapped in against one another. And it's hard to it's hard to visualize exactly what's going on, but these kinds of spindly structures that you do, or that you get by following these out components in space, it gives you a sense of how things are sort of like pinned against one another. Because you imagine you have sort of like a Newton's cradle kind of situation. Everybody knows the Newton's cradle. You have a bunch of particles, they're touching, you slam it on this end, and then the particle jumps off the other end. That collision propagates through all of the internal particles. You're seeing this like disordered Newton's cradle kind of effect, because the thing that's worth noting, one of the things that's worth noting, in addition to this spindly structure on the bottom here, is that this happens, what is this, 5 times, 6 times, 7 times faster in the lower set of frames as in the upper set of frames. So this gives you a sense of the force contact networks inside the structure of the material itself, if that makes any sense.
Yeah. So everything's kind of slipping around each other a little bit to some extent.
Well, the slipping is a bit of a secondary story. I mean, this is totally consistent with no slipping taking place whatsoever. I think what this is, in my mind, the understanding of this figure is that everybody is super crowded together. They just didn't have the time to spontaneously choose a crystalline configuration. So everybody's bumped up against one another, and you try to move this guy and you can't because he's pinned by this one, who's pinned by this one. And it's a heterogeneous environment. So it's not easy to just move spheres one at a time. They're all sort of pinned and connected with one another. And yeah, the slipping past one another is a separate story. And if people care, I can show that figure. Now that you're strictly speaking here voluntarily, if somebody asks me, I will do so. But I won't subject you to it if you're not curious.
Could you please go to that page where you showed this discrete, how should I describe? Can you go?
I can start scrolling and you stop me.
Yeah, scrolling back. Yeah, go back a little, please. No, sorry. Forward, please. I think you showed before this. No, where you had these, three quantities. The third quantity was the time, and you had the basic equation, so to speak, for the simulation.
Oh, for the simulation details themselves, you mean?
Yeah, that one.
This, yeah.
No,
yeah.
No, not this one.
Not this. This?
No. Yeah, this one.
Okay, yeah, this is the construction of the causal graph itself. Yeah, this is a sort of a technically tricky point. Yeah. So what's your question?
I just wanted to go a little more slowly on this page, because I didn't quite catch it.
Yeah, it's complicated, and this page is not super well written. So why don't I just say it again? In my mind, this is sort of the cleanest explanation. So I run a full simulation like this movie here. And at the end of that simulation, I have a list of collisions. Okay, so those can just be arranged by the first collision, then the next collision, then the next collision, and so on, ordered by time, right? And each collision looks like a triple of numbers. This is I'm choosing to define it like this, but this is sort of the minimal definition of a collision. It has a time associated with the collision, and then it has pi and pj, which is particle I, particle j. I'm just numbering my particles 1 to n. So my collision involves particle I, particle j, and time. So now I have a list of these things arranged by time. And then in order to make this graph here, the rule is as follows. I start with particle 1. I go to my list of all collisions and I take out all of the collisions with particle 1. And then I just connect them one by one by one by directed edges. So you can see this a little bit here in this little sequence here. So this collision, particle I collides with particle j at some time. Then particle I collides with particle k at some time. Then particle I collides with particle L at some time. Okay, so All three of these collisions involve particle I. And I don't care about the order of the first two arguments, which probably adds confusion to this. So sorry about that. But the rule is that they're arranged in order of time, and then I just connect them by directed edges. So that's what I do for particle 1, and then I repeat for particle 2, and then I repeat for particle 3. So then when you make this graph, that's why I've colored them in like this. So this is exactly the same graph. I've just colored it in. So if I do this procedure for particle 1, I get this blue subgraph here. And then I do for particle 2, I get the red subgraph. I do for particle 3, I get the green, I think. Yeah, the green subgraph. And then at the end of the day, I make a bunch of individual paths, and then these paths naturally get sort of stitched together just by the rules of this procedure.
Individual paths, you said?
Yeah, so the individual paths, I mean like all of the blue directed edges that move through this graph. You make them one by one, but since each collision involves two particles, every node in this graph will naturally be the meeting point of two of these paths. I can say that more slowly if it helps. But yeah, this is how you should think about it. I take all the collisions, I arrange them by time, then I take out the collisions for particle 1, and I make that path graph, directed graph. Then I take out all the collisions for particle 2, and I make that path graph, and then I repeat for all the particles. And then naturally the structure which gets built is this object here, but the way that it gets built is by like one color at a time, basically, if that makes sense. And then once I have this, then I treat this as a static object that I can do whatever I want with. And that's what we do going forward.
Okay.
It is a complicated point. Sorry about the confusion.
Now it's making more sense. Thank you.
Yeah.
I'm still really interested in the impact of your method. So if I understood you correctly, usually hard spheres representation simulations are done with the other two methods that you'd shown previously, like the network method and this ring graph.
These things here? Yeah.
And you're saying, okay, no, there is a third method that I developed using causal graphs, right? That is the story, right?
Yeah, that's our particular, that's the particular paper that we're writing, is we can use this causal graph, which sort of blends these two approaches, and it gives you certain things of value. Yeah.
Can you tell me of the results that you're getting? Would these other two methods get it to, like, are there results that are just not accessible to these methods because they're lacking the dimension?
Yeah. Okay. So sure. So this top one here, this is the contact network. This is used by a lot of people. This is not at all our invention. This is a common construction. Primarily, the thing that is useful, which kind of comes through in this image here, is you have some disordered solid. So whatever, you have a hard sphere solid, it's tightly packed up against one another, and it's not in some sort of crystalline configuration. The kinds of questions that you ask are like, how many edges does a typical node have? So if we zoom in here, this node has 3 edges coming out of it, and this one is 5 or something like this. You ask for the probability distribution of those things. That tells you something about the spatial structure of this jammed material. So this comes up specifically in the context of jamming studies. These kinds of networks basically only make sense for static pictures of your material. So you have to freeze it in time and then construct this. And what's more, the spheres actually have to all be touching one another. So strictly speaking, there are 2 ways to make that happen. You can add some sort of friction somewhere in the system so that when I push 2 particles together, they don't bounce off one another, but they just stay put. Or I take the pressure to infinity. So I don't care that they're bouncing off one another. I'll just keep squeezing everything until everybody touches. So that's a limit. And there's value to thinking about materials in this limit. It's not a limit that we're taking. This bottom network here, I'm not convinced that there's value to this structure. I mean, there's like, you can investigate this, and it's the kind of thing that would be a good like Wolfram community post or something like that, or maybe a summer school project or something like this. But I think that this is much more something that you can define rather than something that is really helpful to define. I think the causal graph is more useful because it gives you these collision rates, it gives you these out components, and it allows you to look at the spatial structure. This other thing that I didn't talk about, but I'll put on the screen. Sorry for the scrolling here. This thing is another quantity which you can define from the paths, which is this thing I mentioned. If I fix two particles in space, I have another particle bouncing back and forth between them. That's just that particle only ever meets two other particles over the course of its lifetime. But if I allow a particle to meet everybody, then that number will be n-1. This quantity I call the collisional contact number. That's what is plotted here as a function of density. And this you can also extract from the causal graph. So the concise answer to your question is the contact networks give you static information. This intermediate network is an intermediate case, which I'm mostly including for completeness intellectually, but does not offer much value. The causal graph is another case, which is straightforward to define. It sort of harmonizes the two. The advantage is that it can be taken well out of equilibrium, so specifically for time-dependent phenomena. And then you can ask a variety of questions that arguably are hard to answer without the causal graph. And thanks for coming. Somebody's leaving, so thank you.
So your method, causal graph approach, is the only way to get non-equilibrium or far out of equilibrium hard sphere calculations done, probably?
So it's not quite correct the way you say it, although it's in the right direction. So the maybe I don't even need to scroll. The simulation of the underlying physical system can be done entirely without reference to the causal graph. The causal graph is necessarily something that you construct when your simulation has been completed already. The causal graph is a tool which enables a certain perspective. It enables you to ask certain kinds of questions about the non-equilibrium or equilibrium behavior of the system, which otherwise you might not have thought about. So we talked about in the beginning, we have like velocity histograms, and you can ask like, what is the relationship of particles in space and things like this. These are the traditional kinds of quantities that you ask in statistical physics kinds of considerations. And also things like, by the way, the collision rate and the pressure. These are sort of traditional kinds of quantities. The real advantage to the causal graph, to the extent that it has value, is that it raises another set of quantities which might be interesting to look at, but it's not used to speed up the simulation of the system at all. You already have to simulate it. So it's like, once I have my data set, what kinds of questions can I ask, and what does it teach me about the physics story? Does that make sense? So
Yeah. And basically what I'm trying to get to, which I haven't said clearly yet, is like when, as a general physicist, like at what point would I be like, oh no, let's choose a causal graph approach versus a different approach? Like, is that, for example, did you know that you can ask these different types of questions before you even tried the causal graph, or is that just something?
That's a great question. So the causal graph was my summer school project, and I started this. I did not know a single thing about this entire topic of physics. Everything that we've talked about today is something that I've learned in some sense, kicking and screaming while doing this project, trying to teach myself all of the various aspects of it. So what is the advantage of the causal graph? In the grand scheme of things, I think my answer to that question is there is a little bit of an advantage to the causal graph. Specifically in the context of hard spheres, it allows you to raise certain questions which otherwise are slightly awkward to raise. Sorry for the scrolling. Things like this become natural to talk about in the causal graph, where otherwise you can certainly do it. You can do all of this without reference to the causal graph. It's just you might not be led there quite as easily. Most physicists working on hard sphere systems will not have to make a causal graph. One thing that we do say in the paper, which is kind of like a sales pitch, is that it's very cheap to construct these things. It's very easy to modify existing simulations to start recording the causal graph. And it offers a very efficient data compression. So all you need to store is this collision list. Whereas, if you have a system of 4,000 particles and you're storing the state at each time and your simulation has 1 million time steps, you're now talking about gigabytes and gigabytes of data. This is never going to get that big. Take the full case, like, hey, take a look at this object. But, I also don't want to overstate the fundamental significance of this object. I do not think that this object really has that much fundamental significance. I think it is interesting and it has its place, but, compare this to the velocity distribution of the fluid or something like that. I mean, no, it's not of that level of fundamental importance. I see there's a question in the chat. How many particles do we use? 4,096. That's a perfect cube. So we had a cube of particles in a box, and then we went from there. Does that answer your question, Damaris? Okay. Other questions? Thank you all for sticking around for so long. You must have had the longest day of all time. I really appreciate you, and you've been really good participants in this talk. It's been fun. More questions. I see somebody has put a huge amount of stuff in the chat. 2D quasicrystals. I think we've talked about this before at a previous talk.
I might have brought it up. I wouldn't be surprised if I did.
Yeah, this is cool. These topics are like very closely related to all sorts of interesting stuff. For a while in the early years of the physics project, I was pigeonholed on bird flocks because you can simulate bird flocks with very similar tools. And I thought that was so cool. And a few versions of my talk had a little 2D bird flock flying around the screen. This is a little bit deeper than that, but quasicrystals are cool, and that's actually real physics. So.
All right, if there are no further questions, let's thank Matt again for the great talk, and thanks for engaging everyone.
Yeah, thank you very much. It made it much better. I could have spoken to the void and I would have finished my slides, but it would have been much less valuable. So
thanks everyone. Thanks, Matt.
The
recording will be made available, maybe not today, but in a day or two.
Okay, and I will put my slides in Discord forthwith.
Yes, in the lecture recording section.
Fine, that's where they will be.
Thank you so much, Matt.